today would be by Bill Sethares. He will talk about using inharmonic strings in musical instruments. Bill is currently a professor in the Department of Electrical and Computer Engineering at the University of Wisconsin in Madison, and a research scientist in the Conservation Department at the Rijksmuseum in Amsterdam. His research interests include adaptation and learning in signal and image processing with emphasis on the visual and the auditory, and is author of Tuning, Timbre, Spectrum, Scale, published by Springer in 2004, and Rhythm and Transforms, published by Springer in 2007. He has been working in inharmonic strings for the past few years and is excited at the sounds they make. Bill, please, thank you very much for coming.
Amelia, thanks a lot for having us here. This is a wonderful venue, and I'm really honored to be speaking to you all. So I want to tell you about this project that Kevin and Jenyu and I have been working on. It's really exciting. Here's a picture of an actual physical piano. Kevin bought it on Craigslist, ripped the insides out, and then reconstructed it, as you see. I'll show you it in action in a few minutes. The thing that separates this piano from all the other pianos on the world is the strings on a normal piano are uniform. String manufacturers go to great lengths to make the string have the same density all the way across, to be the same width all the way across, to have a harmonic spectrum, have a harmonic sound, fundamental, and the first overtone at twice the frequency, 3 times the frequency, 4 times, 5 times. In this piano, the hyper piano we call it, that's not true. The string does not have a uniform contour. And so this is our first exploration into this area, and I want to show you some of the things, some of the questions that arose as we were working on this, and some of the problems we ran into, some of the solutions we came up with, and I'm really excited because we've solved now, since we wrote this paper, we've solved some more problems, and I'll just briefly mention some of that. So in terms of non-uniform strings, there's kind of 2 extremes that might be familiar to you. At one extreme is the prepared piano. You might think of John Cage. So you take your piano and you stick little clothespins or you stick pieces of metal or forks or rings or you just sort of prepare the piano by placing these obstacles, these sound modifiers on the piano, and you get really different sounds from that piano. It's clangy, it's gongy, it's buzzy, you run out of words to describe it, but it's often interesting. But every preparation is unique because the technique used to prepare the strings is different. At the other extreme, every string, I mentioned the manufacturers attempt to make them perfectly uniform. They attempt to make them perfectly harmonic. And they fail. And they fail in a very small way due to physics. An ideal string that has a harmonic spectrum has no tendency at all to restore itself. A real string, if you drape it over your finger, has a tendency to return to its shape. This nonlinearity causes mild inharmonics in the string. In a normal piano, this is accounted for by stretching the tuning. You take the low notes. Okay, so here's an image from Wikipedia's version on piano tuning. And the low notes are stretched a little bit more. The high notes are compressed a little bit more. And from an actual octave. And so this is inharmonicity in the small. Very teeny tiny amounts of inharmonicity. And so if you think about it, between these 2 extremes, between prepared pianos with their large deviations and wild sounds, and this teeny tiny inharmonicity due to just the manufacturing process of the strings, there's a lot of room. And this room is there to be exploited, potentially. And so the question that was driving this work is, how can we exploit this? How can we control the inharmonicities in the string? How can we control them and make them musically useful? How can we relate the inharmonic sounds that we have from these strings to musical entities like scales or chords that we would like to play? What's the sort of music theory that goes behind inharmonic strings? So here's just the basic physics of the situation. Uniform strings vibrate always with a fundamental, with a first harmonic, second harmonic, third harmonic, and you get this harmonic frequency. When you do not have a uniform string, it's not noisy. Do not think of inharmonic as noise. Inharmonic moves the overtones around a little bit. I've exaggerated maybe here. But the idea is the string is now vibrating, sustaining oscillations in non-integer related fashion. And so right away, you see the big problem here. Harmonic, yes. We know that goal. There's exactly one way to be harmonic. But as soon as you start thinking of inharmonic, there's a whole universe of possibilities. What shaped strings should we use? So let's divide this question of how to make choices into three pieces. Because there's three sort of separate problems that need to be thought about in order to address this. Well, first of all, suppose we had the ability to say, this is the spectrum I want. Then the question would be, how do I build a string to achieve that spectrum? That's a lovely inverse problem. But how would you specify an inharmonic spectrum? Well, if you think about it, there's a bunch of different ways. A bunch of work that I did earlier on looked at the relationship between different n-tone equal temperaments, different ways of dividing the octave into equal pieces, and asking what spectra will sort of sound nice, will have consonant intervals at those points of the n-tone scale. So, for example, think 10-tone equal temperament. The 10-tone equal temperament doesn't have a 500-cent fourth or a 700-cent fifth. It's got a 480-cent interval and a 720-cent interval. How would you make a string how would you specify a spectrum that would have its intervals nicely aligned with those? And this was a problem that has a solution. You can solve it iteratively, or you can solve it for simple cases like n-tone equal temperate strings. You can also specify a desired spectrum from physical objects. So here's one that's really fascinating that I don't know how to do at this point. You know that a clarinet has odd harmonics. A saxophone, say, has all of the harmonics. A string has all the harmonics. Could you design a string with only odd harmonics? That would be to a regular string what a clarinet is to a saxophone. You might imagine an inharmonic spectrum such as given to you by bars, metal bars. That would have a certain overtone structure, such as, say, a xylophone or a glockenspiel might give you. How would you build a string that would have the same characteristics as the bars of a glockenspiel or a marimba? So let's imagine that we're willing to specify our spectrum. Then there's the problem, how do we calculate string parameters? So I'm going to choose a very simple string structure in a second. Focus in on that, which will allow us to do this. But basically, the answer is, this is known. If you think of, the lovely sound of the machine. If you think of we want to calculate the string parameters. So a single string is governed by the wave equation. It turns out that the solution to the wave equation allows variation in the density or contour of the string. Now, it's not the kind of solution that you can just write down in closed form. It's the kind of solution that you have to use a computer to grab and analyze. But this is known, so we can go in the literature and rip this out with sufficient effort. But here's what really kept me from doing this years ago. How on earth am I going to build this thing? I mean, okay. Have you ever looked at how they make strings? They use these winding machines, right? They take a string and then they wind a little wire around it. And they sell machines for, only $10,000 or $12,000 that will do this for you. And they've got all sorts of adjustments to adjust the tension. And so you start imagining, well, gee, maybe I could buy one of these and I could adjust the tension and wind it tighter here and looser here. No, forget. All right. That's not the way to start this project off. So I was talking about this with Kevin, my co-author, and kind of complaining, how am I going to do this? I would really like to build inharmonic strings, but I don't know how to build them. And he said, well, okay, wait a minute. You just told me that they wind them like this, right? Around a core. So what if we unwind it a little bit? If you unwind it, then you have a fat string followed by a skinny string. Or if you unwind it from the other side as well, you have a skinny, fat, skinny string. So, what can you do? What kinds of inharmonicities arise from skinny, fat, skinny? Let's constrain ourselves for the moment to that kind of nonlinearity, whatever it might be, to that kind of inharmonicity, to those kind of spectra that we can get from those, and see where we can go. So, first thing is, now Kevin said, yes, I can unwind these strings. He played around a little bit with it. He found he had to put a little piece of super glue, a little spot of super glue on each end to keep it from unwinding further when you pluck it. But fortunately, super glue is not very massive, so there's no problem. So he could build them. So I had to figure out how to calculate what the spectrum ought to be given the parameters of the string. So let me show you. Here's a little graphic display. It's live. So lambda is my parameter. When lambda is over here, this is the set of roots. All the zero crossings of that little curve there, those represent the modes of vibration, the frequencies at which the string will sound. When it's a string, when the lambda is all the way over to the left, it's a uniform string, all wound. And the fundamentals are at 122, 244, 366, which you recognize as the harmonic series. If we go over here, this is all the way at the other end. Well, that's another harmonic series, in this case, based at around 62. And if you move in between, then you see the relationships are changing. So notice now, at this point, 70 and 160, that's not F, 2F, 3F, 4F. So what you do to play with this one is, okay, that's the harmonic one all the way over there. Here's the one harmonic all the way over there. Very simple additive synthesis. And then you can get a feel for what's happening. Okay, so our first step was to take my calculations. Kevin built his string on a monochord. We recorded it, and we verified that, indeed, the calculations were sound. Well, now we have a problem. How are we going to decide where to put lambda? Now, really, what we have is two lambdas. We have the sort of where the unwinding starts and where the unwinding stops, total length of the string. So we sort of have two parameters that we can play with. Plus, we can, to within the availability of manufactured strings, we can vary the core width and the winding width. Of course, we're stuck, right? We can't do arbitrary, in principle, we could do anything, but we need to do this inexpensively, and so we need to use standard gauges of strings. Fortunately, the manufacturers are happy to tell you what their core size is, what the material is, what the winding is. So from that information, you can mine that, and you can solve that. So what I'm showing here are dissonance curves. So this is if you take the string and you play it against itself at different frequencies, then you get this blue curve, and it sort of represents what intervals sound relatively consonant versus relatively dissonant in this tuning for this particular kind of string. So just as an example, here's the low string, the high string. So that's a relatively dissonant point. Here's not so much. It's not so much beating, not so much roughness. This all comes originally from Helmholtz ideas on harmonics, giving us our notion of consonance and dissonance, refined by Plomp and Levolt in the 1960s. I did some work parametrizing the Plomp and Levolt curves that allow simple drawing of this kind of thing. And so now I gave this to Kevin, and I said, all right, you tell me what you want. So you move through this thing, you can change so now we're changing this, where it starts, where it ends, and we're playing essentially, we can play this string and listen to various intervals. Okay, my interface allows us to go up to higher distances in case we want to see more than an octave. And basically, I said to Kevin, okay, here's the tools I've made for you. What do you want to do? We can't make all these designs. Pick one. And, well, Kevin went ahead and picked one. Okay, so here's a little fuzzy here. I'll show you a better, cleaner picture. Here's the design that he settled on. Notice it's unwound up to about 70% of the string. You can't really see the bottom of it in this photo. It's wound for a short period, about a third or less of the string, and then unwound at the end. That's the design he picked from looking at these things. I'll show you a little bit about the specific design in a second. Here he is after having built this piano now. So that's the hyper piano. It's sitting now in a living room in Indiana. That's Kevin's house. And he plays it occasionally. So pick one, play with it, give it a name. Okay, done, check. Now, here's a close-up of the actual physical construction of the strings on the piano. I mean, you can see what an immense amount of work Kevin did. He actually bought this piano on Craigslist, ripped the guts out, strung it. I'll show you where the fundamentals are of these various strings, and built all of these strings. Here's the front view of it. You'll notice the keys that are pressed are not the original keys, nor in their position, nor are they tuned the way 12-tone equal-tempered piano is tuned. Why is that? Well, that's because the places where the minima of that blue curve that I showed you earlier, the places where those occur for this particular design, are the locations of these keys. So the two directions that we went then were, one is to think about, okay, we've got this cool instrument, we have what's a music theory for this instrument? What does that look like? The other direction is, hey, we've built a cool musical instrument, maybe we could get somebody to compose for it or play with it or something. So those are actually both research directions. So here's a little bit of the theory. I'm not going to spend a lot of time on this because But here's the dissonance curve for a harmonic string. It's a little, I don't know why it's fuzzy there. But if you see the minima of that curve, the one at 1200, well, that's the octave. So what you see is the octave and the unison are the two most consonant intervals. They're at 3/2, 5/3, 4/3. So these are all the familiar just intervals, which are close, arguably, to the normal piano tuning of 12-tone equal temperament. And here on the right is the dissonance curve for the particular string design that Kevin chose. Notice it's got that same sort of undulating feel. Okay, that was sort of the basic criterion by which he chose it. But he chose this particular design for a very particular reason. And that is, you notice it's wider. Well, that's not just the display. This is showing a 2-octave segment in this hyperpiano setup. And so what you see is the notes of the hyperpiano are in red there. And he's named a bunch of them, the sort of hyper fifth, the hyper fourth, the hyper third, okay? And so what this scale system is actually a variation on something that you already know. It's basically like 12-tone equal temperament, but stretched out over 2 octaves. So it's 12 tones per double octave. Notice the actual octave here, the 1200, is not a consonant interval in this system. It's a relatively dissonant interval, and so it actually drives things a little bit like, say, the tritone might drive things in the 12-tone musical system. Okay, that's about all I'll show you. You can do all sorts of stuff. You can think, what if we want an ascending mode and a descending mode? It's got this kind of odd, even kind of feel like a whole tone scale. That you can go from sort of all the even ones to all the odd ones. Okay, anyway, there's a lot of things you can do about that. Let me turn now to the problem of getting people to play it. Okay? So I have some experience here. For many years, I worked with all sorts of different kinds of weird sounds, and I wanted to get people to play with those sounds. And what I would do is I would build a little synthesizer in Max or VSamp or something like this, and I'd say, please compose for my weird sounding thing. And it's a hard sell, right? But now, you know there's a real instrument. Hold that thought. So we contacted a bunch of people, and we came up with a bunch of different possible designs. And I mentioned Giovanni Dettori, who was one of the first people to hop on board and helped us get our software together. And so we created several different MIDI instruments. So what this is this is a Max patch, and this is the particular instantiation that goes in the Ableton Live sequencer. So this is a Max for Live device, so that if you happen to be running Ableton Live, you can stick this particular thing in there, and then as you play your MIDI numbers, it triggers this keyboard here, which is the notes of that were in red in that previous thing. And it's just basically a sample. We sampled all the strings of the piano. We recorded those. They sit in a file, and when you press the piano, it triggers the appropriate sample. So it works like a regular sampler, like a simple regular sampler. Plus, you have some tuning thingies that you can futz with, because if you're an electronic musician, you never like the way it sounds exactly. You always want to play with it. So there's a few simple controls there. Of course, in the live environment, you can also string along any other live reverbs or phasers or whatever it is that you like to do. So we created, so on the website for this paper, you'll find this implementation, the original Max patches. You'll find a VSamp, which is another kind of plugin that plays samplers, and a couple of other versions of this. And we sent these out to basically everybody we could think of who we thought might respond favorably. And so we asked for comments as people were doing it. People were often had quite interesting things to say about how their compositional process interacted with the software and with the musical system that the software embodied. Giovanni was, as one of our first guinea pigs, Giovanni was particularly useful in terms of helping us shape things so that we could overcome the problems of our earlier instantiations. And here's the people that we were able to convince to compose for us. I don't feel like I have a lot of time to do this, but here's just a few. Different takes on what you might do with this. And so this is one way that so here's, as far as I know at the moment, all of the different compositions that have been created in this tuning for this piano. And we would like to invite you people to join us in this exploration, if you would. So Kevin's kind of old school. And he thinks like CDs are really cool. So, look, as a souvenir of your trip here to please pass these out. And there's a few more if they don't get around. Now, because you're all digital people, you can also listen to this at the website. You can click and download these pieces, okay. But Kevin made me take all of these things and promise not to bring any back. So you have to help us here. Okay, so let me tell you about the two things that I think, looking forward, are the most exciting about this process. Here, so far, I've talked about one particular design. And it's a design that basically Kevin picked kind of by playing with those little Mathematica notebooks and, just listening and thinking about things. There's a lot of ways, as an earlier slide commented, to be inharmonic. And so the direction that we're moving right now is to solve the inverse problem. That is the problem given a specified desired spectrum. So think maybe the spectrum for a metal bar. Think the spectrum that a Bonang in a Javanese gavilan has. Think an n-tone equal tempered variation of a harmonic spectrum with consonant intervals at those steps of the n-tone equal tempered scale. Think whatever you want as a desired spectrum. How do we go from that desired spectrum back to a string contour? Well, if you think about it, actually, the answer's, there's an easy answer. And the answer is this. We know how to calculate the forward direction. Given a set of string parameters, unwrappings like this, little weights that you might add to the string. Given a set of string parameters, you can just calculate what the spectrum is. So, for a fixed structure, what you could do is guess, see what the spectrum is, guess again, modify your guess a little bit. Maybe if you're clever, you could go in a gradient or pseudo-gradient direction, and then slowly converge to, hopefully, a good answer. So it turns out this actually works. So when we wrote the paper for this conference, we did not have it working. We had one example that we had finagled by hand. So let me show you that example. That was for a 10-tone piano string. And to do that, this required, you see the structure, the geometry of the string up here. It's one string, and we don't just unwrap it once from each side. We also unwrapped it in the middle a little bit. And just by playing, so how many parameters are there here? Well, there's one length for each of those things, and there's two mu ratios for the densities. So that's, 5 or 6 parameters. Humans work okay in 5 or 6 dimensions, it turns out. If you want to do more complicated things, you got to go back to the computer and have it solve it the real way. But for this application, since this was relatively recent, we had just one piece. So here is the piece in the 10-tone equal tempered. We built one string, okay, to be honest here. We built one such string. We plucked it, verified that it had the spectrum that we had claimed from the simulations, and then sampled that string a couple different ways and turned that into a similar max patch. And here is a piece by Dervigia. So you can hear the non-12 intervals pretty clearly. And of course the percussion is not the string. Okay, and it goes on. Kind of goes on. It sort of develops as if it was a piece of music and stuff. So that MIDI instrument that he used to create that is also on the website. And the final thing I want to say is all of these designs that I've talked about are for one single string. And then, of course, you can build a rank of strings. Turns out, if you have a string, you can adjust the fundamental pitch or the ratio of all the pitches by lengthening it. So percentages in that thing which had certain percentages, if you just make everything longer, the pitch goes down proportionately, just like with a harmonic string. Or you can increase the tension. That also has the same effect. It leaves the spectrum unchanged. And, interestingly, the ratio of the densities remains unchanged. So you have 3 separate mechanisms for retuning strings. And the direction that I would really like to go in next is the direction of designing strings for fretted instruments. Why is that different? Well, if you think about it, now you have a single string, and instead of a nicely scaled string by tension density or instead of a nicely scaled string size, you're cutting the string and making it shorter as you fret the instrument. What that does is it changes all those ratios. It changes the timbre. So this would be an instrument in which each note has its own timbre. And so the question is, and I don't have an answer for this at the moment, but the question is, how do we go about designing those kind of instruments? Because if it's possible, it's going to be a lot easier to manufacture them than it is to manufacture. Pianos are big. They're hard to move around. So fretted instruments would be, I think, much a superior way of using inharmonic strings in the future. Okay, so that's what I wanted to talk about.